Welcome back to the physics module. Let's do a quick recap of the stuff we've covered so far. In our last video, we looked at the double slit experiment and discovered the bizarre reality of superposition. We learned that a single isolated electron doesn't actually travel like a tiny baseball. It travels as a spreading wave, allowing it to pass through multiple paths and exist in multiple states at the same time. But we also discovered a massive problem, the observer effect, which tells us that the instant we place a camera or a detector next to the experiment to see what the electron is doing, the superposition is instantly destroyed. The wave, quote unquote, collapses, and it acts like a boring normal particle again. This is known as the measurement problem, and it leaves us with the biggest question in all of quantum mechanics. If the electron is a massive spreading wave covering the entire room, how does the universe decide exactly where the solid particle is going to appear when the wave collapses? Einstein famously hated this idea. He said, God does not play dice with the universe. But as it turns out, Einstein was at least kind of wrong. In 1926, a physicist named Max Born figured out how exactly the universe loads the dice. He realized that the collapse of a quantum wave isn't purely random. It's directly tied to the physical shape of the wave itself. We call this the Born rule. For example, let's say our electron, when it's a wave, looks something like this. From now on, we'll be referring to this wave as the wave function of the electron. On the left side, the wave has a massive peak, but on the right side, the wave is really shallow. If we observe this electron, the wave instantly collapses. Because the wave was physically highest on the left side, there might be, say, a 90% chance that the solid particle appears over there. And because the wave was shallow on the right side, there's only about a 10% chance that it appears there. And if there's a spot where the wave completely cancels itself out to zero, it's physically impossible for the particle to ever appear there. Now, we can never predict where exactly the particle will land with 100% certainty. Now, we can never predict exactly where the particle will land with 100% certainty, but the Born rule gives us the exact mathematical probabilities. But this physical reality bothered a lot of scientists. If microscopic things like electrons and atoms can exist in these spreading waves of multiple possibilities, why don't everyday objects do the same thing? Why don't we see baseballs or chairs or cats in two places at once? To try and explain this, a scientist named Erwin Schrödinger came up with one of the most famous thought experiments in history, which you actually might have heard of, called Schrödinger's cat. Imagine we take a completely sealed and soundproofed box. Inside the box, we place a single radioactive atom. We know from physics that this atom is a quantum object in a superposition. In the next hour, let's say that there's a 50-50 chance that the atom will decay and release radiation. So the wave function of the atom might look something like this. Next to the atom, we put a Geiger counter, a device which measures radiation. If the Geiger counter detects radiation, it then drops a hammer, which smashes a vial of poison, which kills the cat sitting inside the box. The question Schrödinger asks us is, if we close the box and wait exactly 1 hour, what state will the cat be in? Classical logic says that the cat is either dead or alive. We just don't know yet because we haven't opened the box. But quantum mechanics says something entirely different. The radioactive atom isn't just a 50-50 coin. Until we look at it, it's in a superposition. It has both decayed and not decayed at the same time. Because the Geiger counter's fate is directly tied to the atom, the Geiger counter enters the superposition as well. This means that it has both dropped the hammer and not dropped it, which then means that the poison is both broken and unbroken, which means that the cat is both entirely dead and entirely alive at the same time. The entire macro-sized box has now become entangled in a massive quantum wave of probabilities. And the idea of measurement collapsing the system also makes a lot of sense in this experiment. Once we open the box or we take a measurement, the superposition is broken, and the wave function here collapses to one state. Either the cat is dead, or the cat is alive. An important thing to note here is that there's no way to cheat the system and measure without collapsing the system once and for all. For example, if the box wasn't 100% soundproofed and we were actually able to hear the glass shatter when the hammer breaks the file, then we would once again collapse the system. Now, obviously, you've never seen a cat which is both dead and alive in real life. So where does Schrödinger's logic break down? Why does the macroscopic world look so normal if it is entirely built out of quantum particles? The answer to that is that it breaks down due to a concept called decoherence. When we talk about the observer effect, a lot of people think that it requires a conscious human brain, that a human eyeball has magical powers that collapse the wave somehow. But this isn't true at all. In quantum mechanics, observation just means interaction. If an electron is in a superposition, it is incredibly fragile. Even if a single stray air molecule bumps into it, the universe has just observed it, and the wave will collapse. If a single photon of heat from the sun touches it, the universe has observed it, and again, the wave function will collapse. A cat, however, is made up of trillions and trillions of atoms, which are constantly bumping into each other and interacting, which means that macroscopic objects are constantly measuring themselves. The wave function collapses billions of times every single second before it even has a chance to spread out, meaning that the quantum effects we studied just end up decohering into normal, boring classical physics. So now we understand superposition, and we understand how measurement causes superposition to collapse. Now there's only one piece of pure physics left which we need to study before we get into quantum computing. In our next video, we'll take a look at what happens when two separate superpositions get permanently tangled together, the concept known as quantum entanglement. I'll see you then.